Yeah, thank you very much. I'm going to start the section on generative AI, and my background is natural language processing, so thanks to Callum, he already mentioned a couple of keywords from this area that has seen tremendous progress in the recent years. In my talk, I'm going to focus on 3 points. So first, I'm going to give you some insights into foundation models, which are at the core of current natural language processing. Then recent trend, prompting, that makes this technology even more powerful. And at the end, I'm going to talk about challenges and the potential of quantum AI for NLP, though these fields are currently almost completely disconnected, so there's no joint research yet, but for a few exceptions. So first, let's talk about the so-called foundation models. Actually, they have been around for a couple of years, since 2019, when BERT, a large language model, has been published. But the term foundation models has been coined last year at Stanford. What are foundation models? Foundation models are huge models having billions of parameters that are trained on very large amounts of textual data, and that can be adapted to a wide range of downstream tasks. Examples of such models are GPT-3 or OpenAI's DALL-E or BERT. And what makes them work? First, the scale of data which is used for training such models. They are trained on huge amounts of text data, which is typically collected from the internet sources, using a special method called self-supervision. So that's actually the technological game changer related to the big data, because they can be trained automatically, fully automatically, based on big amounts of data. And then once we have such a big model, so you can imagine it learns a lot of general language knowledge that we humans intuitively have in our mind. Such a model can be adapted and transferred to many downstream applications. Examples are machine translation or text summarization, information extraction, or natural language generation. How does it work? We have this implicit supervision task, which is called masked language modeling. Basically, we take a sentence, for example, and then we mask a token that is a word in this sentence, and then we try to predict the missing word. And since we have a lot of data, we have a lot of such examples, and there is no manual work involved. Such a model is very rich in its capacity to represent language, but also has a huge number of parameters. Now, more recent trends is to make this technology even more powerful, so it's called prompting. So as already mentioned in previous discussion, the availability of training data for specific applications is very often a bottleneck. So the basic idea behind prompting that we can interact with this language model, which is a huge artifact, with the help of natural language that we call short text instructions or prompts. So such a prompt can be, for example, translate English to French, and we give this prompt as input to the system, and we give a couple of examples of translations from English to French, and then we ask for an English word, what would be the translation? And this model can automatically, based on the instruction and a few examples, perform the same task. The underlying idea of prompting is that we model the task in a way which is related to this self-supervised training, which I have already explained. So the model is automatically converting this instruction and examples to a sort of more complex and more rich self-supervised training, and this is how such a task can be learned with the help of prompting and a few examples, and then the model can easily adapt to different tasks given and generate the correct output. In the meanwhile, we have a lot of various applications of prompt-based generation specifically. So this is growing quite massively, and many people bet on this technology. So what can we do with it, but for generating language? For example, we can automatically generate software code based on this technology, because software code is also like a textual representation having specific semantics, and there are systems like Codex or GitHub Copilot where people can give a natural language prompt and the system can generate the code. And the same is for image generation. There are systems like DALL-E or Stable Diffusion. And here I have an example of such code generation via prompting, where a textual prompt is given and then the computer code is generated automatically based on a large amount of computer code available for training. And another example is Stable Diffusion, which generates an image based on this prompt, a pencil sketch of robots playing poker. So then the computer would generate automatically the image corresponding to this prompt. Now, to conclude, a few remarks on challenges and the potential of quantum AI from my perspective, though I've never worked on it seriously, just a few thoughts. So one immediate thought, of course, in line with the topics discussed here, is that the capacity of language model and their performance has been growing steadily due to the availability of huge computational power. And there are all the time new models entering the arena, like GPT-4, which has even much larger space of parameters. And we feel that most recent models are close to an upper bound of what can be achieved by this technology, limited by the existing hardware. Of course, these models become ever more expensive in computation, and there are environmental effects, and there's just the economic cost of training such a model. So this is a big challenge in this field. So my slide is not moving anymore. There you go. Thank you. And one obvious idea is that quantum AI could substantially alleviate these efficiency issues and make much larger computations possible, leading to further progress. No? Okay. Another thought is that we have models that struggle to express proper uncertainties, and, well, human life in general, but language in particular, is full of uncertainties. So there are representational formalisms and algorithms like Bayesian deep learning that can provide much richer representation and learning capability. However, these are very computationally expensive, so they are not computable for large data given today's hardware, and they're very costly. And if we could compute such algorithms, then natural language processing will see a paradigmatic shift, because it will become much more powerful due to the capability of modeling uncertainty. Here, quantum AI could be a possible solution for applying such algorithms in practice, and of course there are many more algorithms that could be experimented with here. And a few thoughts that I collected just on the trade-offs of quantum computing, NLP, and AI in this symposium, I'd like to include them just to summarize my impressions so far. So what I understand is that to do really practical work on NLP with quantum computing, we are currently lacking some crucial infrastructure. So, for example, the hardware, because we are a practical field, so we need to provide like an implementation and run experiments on different tasks, but this is not yet possible due to the unavailability of the hardware. However, the opportunities arise not only from the efficiency and the scale of computation, it's also because quantum computing works differently from traditional computing. We can compute logical operators that could not be previously computed. So if we understand how to use these additional capabilities of quantum computing to enable new things in AI and natural language processing, I think that could also lead to a paradigm shift and further performance improvements in the field. Thank you very much.
Thank you very much.